This next example is from a pretty recent free response section of an AP test. We have two functions. F of x is quadratic, so it graphs a parabola. G of x is a cosine curve, and we've been given the graph. That's nice. We've been asked to find the area enclosed by the region. So you can see label R, section or region R is labeled pretty clearly. And here the trick is not the limits. They've been pretty clear in the picture that the furthest most x is x equals 0. The furthest right x is x equals 2. So it's clear where these graphs intersect. We're going to have to write an integral for this area, one or more integrals. So let's check it out. If we always have the same curve on top, we always have the same curve below, then we can just go straight to that expression that's at the bottom of your first page. We're going to integrate from left to right of top minus bottom. So I'm going to trace along the upper edge of the region. So was I always tracing along the same curve? I was, and that happens to be g of x. That's the cosine curve, that's the upper bound of that region. When I trace along the bottom, I'm going to trace here. Oh, I missed a little bit, but that is always the same curve. The bottom curve doesn't change. It's always f of x, the quadratic curve, the parabola. So this is the integral I'm going to write. All right, so I'm going to integrate from left to right of top minus bottom, and I don't have any problems here. G of x is always the top curve. It's been given as a function of x. F of x is always the bottom curve. It's already a function of x. I would get 1 point just for writing this expression. And notice I don't even have to copy out the complicated g of x and f of x functions that I've been given. So at the very least, get this integral onto your paper for 1 point. Now for 3 more points, this is where the work on this problem comes, we're going to actually do this integration. So the g of x function, that's the one that's on top. And notice that I have that cosine of something kind of complicated. I'm going to have to make a u substitution on this problem. So I'm going to write the second integral here. So I'm going to split this up into 2 separate integrals because I'm going to need a u substitution for the first integral that I don't need on the second one. That second integral is actually pretty easy to find an antiderivative for. But this first one's going to be a little bit complicated. So let's see, where's my u substitution? So I'm going to make the u substitution. U is pi x over 4. I'm going to take the derivative of both sides. I'm going to get du is pi over 4 dx. And then in order to isolate dx, I'm going to get 4 du over pi. And remember, I'm only making this substitution in the leftmost integral. The right integral, he's going to be fine just the way he is. Let's see. There we go. So my next step, notice I have updated my limits. If u is pi x over 4, I'm going to plug in my original lower limit was 0. I'm going to plug in 0 to my little u function. U of 0 is going to be pi times 0 over 4, which is just 0. When I plug 2 in, u of 2 is pi times 2 over 4, which simplifies to pi over 2. That's how I got this new upper limit as I change from x's to u's. So the 4 was there. Cosine of pi x over 4 becomes cosine of u. And I'm going to replace this dx with this expression for dx. So that's how I get this new first integral. The second integral I'm just leaving alone for a second. So notice some things. Oh, well, hey, there's actually not anything that cancels out. Huh. But, I mean, you might have expected. I bet a lot of people on the day they took this test, they thought that the 4s would cancel each other out. But notice I have a 4 here, multiplying a 4 here. This pi in the denominator doesn't have anybody to cancel out with, so I'm going to have a 16 pi factor that I could bring out in front of my integral. The antiderivative of cosine of u is just a sine of u. So here's my antiderivative. going to be 16 over pi times the sine of u, which I'm going to evaluate from 0 to pi over 2. And I'm going to subtract what I get when I evaluate the antiderivative of the second integral from 0 to 2. So the antiderivative of 2x squared is 2x cubed over 3 minus 3x squared plus 4x. All right, so I'm going to clear some of this stuff out of the way so we can evaluate this integral. All right, so now I have my antiderivatives I'm actually going to evaluate. So I was evaluating 16 over pi of sine of u from pi over 2 to, so from 0 to pi over 2. So I have 16 pi sine of pi over 2 minus 16 pi sine of 0. And I'm going to subtract the result of evaluating that second derivative from 0 to 2. So you can see I've come through here and I've replaced all the x's with 2's. And I'm subtracting what I get when I replace all the x's with 0's. So 16 over pi sine of pi over 2. Well, sine of pi over 2 is 1. So that all evaluates to 16 over pi. Sine of 0 is 0, which is why I have nothing else left there. And then inside the parentheses, I'm going to have 16 over 3 minus 12 plus 8. These guys all evaluate to 0. Recall that you could have left, well, we do need to evaluate the trigonometric functions. So you needed to show that 16 over pi times sine of pi over 2 is 16 over pi. And the rest of this you could have left unsimplified. So this would have been a totally correct answer you could leave on a free response section. If you go through the process and actually simplify, you get 16 over pi minus 4 over 3. So you'll notice when you take your AP test, there's a whole wide range of ways that this topic, areas between curves, can get tested. Sometimes they're testing really tricky things about how to find the limits, and then we'll show you an example next where we're going to have to actually use our calculator to find the limits. There are sometimes when the problem is all about figuring out how to break up the curve into separate regions and integrate because your top curve or your bottom curve isn't always the same. On this problem, the real trick here was the integration because we needed that u substitution, and this was a non-calculator problem. So as long as you've got this idea that when we can, we're going to integrate from left to right of top minus bottom, then we're just going to put into use all of our practice we've been doing finding antiderivatives.